Welcome to this video. Today, we'll dive into an exciting algorithm problem titled 4 Keys Keyboard. Together, we'll explore how to determine the maximum number of A's that can be printed on a screen with a given number of key presses. Let's get started. Imagine you have a keyboard, but it only has 4 keys. The first key, A, simply types the letter O on the screen. The second key, Control A, selects all the text currently on the screen. The third key, Control C, copies the selected text to a clipboard, which can store the copied content temporarily. Finally, the fourth key, Control V, pastes the content from the clipboard onto the screen. Now, the challenge is this: you start with an empty screen and an empty clipboard, and you are given exactly n operations to perform. Your goal is to use these keys in a way that maximizes the number of A's displayed on the screen after completing all n operations. To solve this, you'll need to write a function called maxa that takes the input n and returns the maximum number of A's you can achieve on the screen. Let's look at an example to understand the problem more clearly. Suppose you are allowed 3 operations, so n equals 3. In this case, the optimal sequence of operations is to press the A key 3 times. On the first press, the screen will display 1 A, and the clipboard will remain empty. On the second press, the screen will display 2 A's, and again, the clipboard remains empty. Finally, on the third press, the screen will have 3 A's. Since there is no time to use the clipboard effectively with only 3 operations, simply typing A each time is the best strategy. The result is a total of 3 A's displayed on the screen. Now, consider a slightly larger example where you are allowed 7 operations. Here, the optimal strategy becomes more interesting. First, you press A 3 times, which gives you 3 A's on the screen. Then, you use Control A to select all the text on the screen, followed by Control C to copy it to the clipboard. At this point, the clipboard contains 3 A's. Next, you press Control V twice, pasting the content of the clipboard onto the screen each time. After one paste, the screen shows 6 A's, and after the second paste, the screen displays 9 A's. By strategically using the clipboard, you achieve a total of 9 A's in 7 operations. Let's explore an even larger example, where n equals 11. To maximize the output, you begin by pressing A 3 times, resulting in 3 A's on the screen. Then, you use Control A to select all the text and Control C to copy it to the clipboard. After that, you press Control V 3 times, pasting the clipboard content onto the screen with each operation. This increases the count to 6, then 9, and finally 12 A's. Next, you use Control A again to select all 12 A's on the screen, followed by Control C to copy the new content to the clipboard. Finally, you press Control V one last time, doubling the total number of A's on the screen to 27. By carefully planning the sequence of operations, you achieve the maximum possible output. To ensure we understand the constraints and requirements, let's summarize a few key points. First, the input n can range from 1 to 50, and the challenge is to determine the optimal sequence of operations to maximize the number of A's on the screen. Any combination of the 4 keys is allowed, but not all combinations are efficient. For smaller values of n, such as 1 or 3, the best strategy is simply to press A for all operations. However, for larger values of n, using the clipboard becomes essential, and you need to decide the right moment to use Control A, Control C, and Control V in your sequence. Let's also consider some specific edge cases. For the smallest input, where n equals 1, you can only press A once, resulting in a total of 1 A on the screen. When n is small, such as 3, there is no need to use the clipboard, as typing A repeatedly is the most efficient approach. However, as n increases, the clipboard becomes increasingly important. By strategically using the Control A, Control C, and Control V sequence, you can multiply the number of A's on the screen significantly. The challenge lies in determining the optimal sequence of operations to achieve the maximum result within the given constraints. The 4 keys keyboard problem challenges us to maximize the number of A's printed on a screen within a fixed number of key presses, using 4 operations: typing a single A, selecting all text, copying the selected text, and pasting from the clipboard. While typing A repeatedly is straightforward, it becomes inefficient as the number of key presses increases. The key to solving this problem lies in leveraging the copy-paste operations, which allow exponential growth in the number of A's. The strategy involves identifying when to use the key combination of Ctrl-A, Ctrl-C, and Ctrl-V for maximum efficiency. These operations involve a trade-off. They consume multiple keystrokes to set up but can yield significantly higher returns through repeated pasting. Typically, the optimal approach begins by typing a few A's to establish a base, then strategically using Ctrl-A and Ctrl-C to copy the current content when it becomes more beneficial than typing, followed by repeated pasting to maximize output. The essence of the problem boils down to finding the right moments, or breakpoints, where using these operations provides the highest payoff. To solve this problem, we can consider several approaches. One is the brute force method, where we simulate all possible sequences of operations for a given number of key presses. At each step, we recursively explore all 4 operations and calculate the maximum number of A's achievable. However, this approach has exponential time complexity, making it computationally infeasible for larger values of n. While impractical, it helps us understand the problem structure. A more effective approach is dynamic programming. Here, we define a DP table where DP, I, represents the maximum number of A's achievable with exactly I key presses. For each key press count, we evaluate all possible points where we could use Ctrl-A and Ctrl-C, followed by a series of pastes. The key formula involves maximizing DP, J, asterisk, IJ1, where J represents the point of copying and IJ1 accounts for the number of pastes. This method has a time complexity of O, n squared, as we calculate the optimal solution for each state by iterating through all previous states. It's both efficient and guarantees an optimal solution, making it a strong candidate. Another approach to solving the problem involves mathematical insight and greedy optimization. This method is based on the observation that the optimal strategy often involves breaking the problem into segments that maximize the product of their lengths. For larger values of n, this approach approximates the solution by focusing on factorization and chunking the operations into smaller, efficient pieces. While it has a linear time complexity and provides a theoretical shortcut, it can be challenging to generalize and apply in a systematic way without deeper mathematical analysis. Ultimately, the dynamic programming approach stands out as the chosen strategy due to its balance of efficiency, clarity, and practicality. It allows us to systematically build solutions for smaller subproblems and scale up to the optimal result with manageable computational effort. Compared to brute force, which is computationally prohibitive, and mathematical insight, which lacks intuitive implementation details, dynamic programming provides a well-rounded solution that is both scalable and guarantees optimal results for practical input sizes. To tackle the 4 keys keyboard problem, our objective is to find the maximum number of A's that can be printed on the screen with exactly n key presses. The operations available are straightforward. Pressing key 1 types 1 at, key 2 selects all text, key 3 copies the selected text, and key 4 pastes the copied text. A key insight is that the combination of Ctrl-A, Ctrl-C, and repeated Ctrl-V operations enables exponential growth of A's on the screen. However, for small values of n, such as when n is less than or equal to 6, typing A repeatedly is more beneficial because there aren't enough key presses to take advantage of copy-paste operations. This sets the stage for understanding how to balance these operations over a fixed number of presses to achieve the maximum output. The dynamic programming approach is a structured method to solve this problem. We define a DP array, where DP, I, represents the maximum number of A's that can be printed with exactly I key presses. The base case is simple, DP, 1 equals 1, since pressing key 1 once results in 1 A. For values of I greater than 6, the optimal strategy involves a sequence of Ctrl-A, Ctrl-C, and multiple Ctrl-V operations. The transition formula, dp, I, equals max, dp, j, asterisk, ij1, calculates the maximum result by considering all possible breakpoints j, where j is the point of the last Ctrl-C, and ij1 represents the number of Ctrl-V operations that follow. To implement this, we initialize the dp array, set dp, I, equals I for small values of I, and for larger values, iterate through all potential breakpoints to compute the maximum value. The result for dp, n, gives the desired maximum number of A's. When analyzing edge cases, it's important to consider scenarios like n equals 0, where no key presses are possible, and the result is simply 0. For small values of n, such as when n is less than or equal to 6, the algorithm directly assigns dp, I, equals I because typing A repeatedly is optimal. A key insight here is understanding how the sequence of Ctrl-A, Ctrl-C, and Ctrl-V creates exponential growth. The earlier the Ctrl-C operation is performed, while still leaving enough key presses for subsequent Ctrl-V operations, the more significant the growth. This approach leverages the optimal substructure property, where solving smaller subproblems like dp, j, contributes to the solution of larger problems. Finally, there's a trade-off to consider. While typing is faster for small n, copying and pasting become far more effective as n increases. The dynamic programming array is the core data structure used here, storing the maximum number of A's that can be printed for each possible key press count from 1 to n. As we iterate through each value of I, we calculate the optimal result by evaluating all possible breakpoints j. Variables help track these breakpoints and maximize the value for each I. The algorithm involves three key operations: initializing the dp array to store results for subproblems, iterating through each I to compute the maximum possible value, and using the max function to select the best result for each step. This systematic approach ensures that the solution is both efficient and correct. In terms of time complexity, the outer loop runs 4n iterations, and the inner loop evaluating breakpoints runs for up to n3 iterations, leading to an overall time complexity of O(n squared). The space complexity is O(n), as the dp array requires storage proportional to the input size. The pseudocode for this algorithm encapsulates all the discussed steps. The function maxes starts by checking if n is less than or equal to 6. In that case, it directly returns n, as typing it repeatedly is optimal. Otherwise, it initializes a dp array of size n+1 to store intermediate results. For each I, the algorithm computes the maximum number of A's either by typing directly or by evaluating all possible breakpoints j for the last Ctrl-C. The formula dp I equals max dp j asterisk I j1 ensures that the optimal value is selected at each step. Finally, the function returns dp n, which represents the maximum number of A's achievable with n key presses. This approach is both efficient and scalable, ensuring that even for larger values of n, the solution can be computed in quadratic time with linear space. This solution implements a dynamic programming approach to solve the 4-keys keyboard problem. The key idea is to maximize the number of A's produced using the available key presses. We define a dp array where dp I represents the maximum number of A's that can be achieved with exactly I key presses. Algorithm explanation. 1. Initialization. Create an array dp of size n+1 initialized to 0. This array will store the results for subproblems. 2. Iterate through key presses. For every number of key presses I, from 1 to n, calculate the maximum possible A's. Option 1. Press A once. This means dp I equals dp I1 plus 1. Option 2. Use the sequence Ctrl-A, Ctrl-C, followed by multiple Ctrl-versus. This requires choosing a prior point j, 2 to I1, where Ctrl-A and Ctrl-C are performed. After that, pasting happens, j, times. The resulting count is dp j2 asterisk j plus 1. 3. Update the dp array. For each I, calculate the maximum value between the two options. 4. Return the result. After populating the dp array, the result is stored in dp n. Complexity. Time complexity. The outer loop runs n times, and the inner loop runs up to n in the worst case. Hence, the overall complexity is O(n squared). Space complexity. The solution uses an array of size n+1, so the space complexity is O(n). This approach ensures that all possible combinations of operations are considered, leading to the optimal solution. This is the Java implementation of the 4-keys keyboard problem from LeetCode. The logic mirrors the Python solution by using dynamic programming to calculate the maximum number of A's that can be produced with a given number of keystrokes. Key differences include explicit type declarations, the use of Java's math.max function for comparisons, and Java's array-based approach for dynamic programming. The main method provides an example for testing the function directly. The 4-keys keyboard problem challenges us to determine the maximum number of A's that can be printed on the screen using exactly n keystrokes. The only operations allowed are pressing the A key to print a single A, using Ctrl-A to select all content on the screen, Ctrl-C to copy the selected content to the clipboard, and Ctrl-V to paste the content from the clipboard onto the screen. Our goal is to maximize the number of A's printed by strategically combining these operations. To solve this, we'll use a dynamic programming approach, where each dp, I, represents the maximum number of A's we can achieve with I keystrokes. For example, with n equals 3, we initialize our dp array as 0, 0, 0, 0. The first keystroke is pressing A, which gives us dp, 1 equals 1. The second keystroke presses it again, resulting in dp, 2 equals 2. Finally, the third keystroke presses A once more, making dp, 3 equals 3. Thus, with 3 keystrokes, the maximum number of A's we can achieve is 3. Now, let's explore the case where n equals 7. First, we initialize our dp array as 0, 0, 0, 0, 0, 0, 0, 0. For the first 3 keystrokes, we simply press A, resulting in dp, 1 equals 1, dp, 2 equals 2, and dp, 3 equals 3. At this stage, the array becomes 0, 1, 2, 3, 0, 0, 0, 0. For the fourth keystroke, pressing it gives us dp, 4 equals 4. Similarly, the next keystroke results in dp, 5 equals 5. By the sixth keystroke, we explore using Ctrl-A, Ctrl-C at j equals 4, and then pasting twice. This results in dp, 6 equals dp, 2, asterisk 3 equals 6. Finally, for the seventh keystroke, we use Ctrl-A, Ctrl-C at j equals 5 and paste twice to achieve dp, 7 equals dp, 3, asterisk 3 equals 9. The optimal result for n equals 7 is thus 9, as shown in the final array, 0, 1, 2, 3, 4, 5, 6, 9. Now, let's look at an example with n equals 10. Here, the dp array is initialized to a size of 11, filled with zeros. For the first 6 keystrokes, we press A repeatedly, giving us dp, 1 through dp, 6, as 1, 2, 3, 4, 5, and 6, respectively. At the 7th keystroke, we use Ctrl-A, Ctrl-C at j equals 5 and paste 3 times, resulting in dp, 7 equals dp, 3, asterisk 3 equals 9. For the 8th keystroke, we use Ctrl-A, Ctrl-C at j equals 5 and paste 4 times to get dp, 8 equals dp, 3, asterisk 4 equals 12. Similarly, for the 9th keystroke, using Ctrl-A, Ctrl-C at j equals 6 and pasting 3 times gives dp, 9 equals dp, 3, asterisk 4 equals 12. Finally, at n equals 10, using Ctrl-A, Ctrl-C at j equals 7 and pasting 3 times gives dp, 10 equals dp, 4, asterisk 4 equals 16. Thus, the maximum number of A's we can achieve with 10 keystrokes is 16. The key insight from this problem is understanding when to switch from pressing it to using the combination of Ctrl-A, Ctrl-C, and multiple Ctrl-V operations. The optimal strategy involves carefully selecting the point where copying and pasting becomes more beneficial than continuing with individual presses. Dynamic programming allows us to compute the maximum number of A's for each keystroke by leveraging previously calculated results, ensuring an efficient and structured approach to the problem. This way, we can determine the best sequence of operations to maximize the output for any given n. To analyze the time complexity of our solution, we begin with the outer loop, which runs from 1 to n. This means there are n iterations in total, and this contributes O(n) to the time complexity. Within each iteration of the outer loop, we have an inner loop that runs from j equals 2 to I-1. In the worst case, the inner loop could run up to I iterations for each value of I. When we sum up all these inner loop iterations across all values of I, it forms the sum of the first n natural numbers. Using the formula for the sum n times n-1 divided by 2, we can see that the total number of iterations is proportional to n squared, or O(n squared). Now, inside the inner loop, we perform operations such as the max function and a multiplication, both of which take constant time, O(1). This means the total cost of the inner loop is dominated by its number of iterations, which is O(n squared). When we combine the contributions from both the outer and inner loops, the overall time complexity of the solution is determined to be O(n squared). Moving on to the space complexity, this is primarily influenced by the dynamic programming array, or DP array. This array has a size of n+1, as it stores the maximum number of A's achievable with I keystrokes for all values of I from 0 to n. The space required to store this array is O(n). Additionally, no other data structures are used, and the algorithm operates directly on the DP array. This means the auxiliary space complexity is constant, or O(1). When we combine these, the overall space complexity of the solution is O(n). To better understand the efficiency of the dynamic programming solution, let's compare it with a brute force approach. A naive solution would involve simulating all possible keystroke combinations for n operations. Since each operation has multiple branching possibilities, such as pressing or using Ctrl-A, Ctrl-C, and Ctrl-V, the total number of combinations grows exponentially, leading to a time complexity of O(2 to the power of n). In contrast, the dynamic programming solution optimizes the problem by breaking it into overlapping subproblems and storing intermediate results. This reduces the time complexity to O(n²) and the space complexity to O(n). Mathematically, we can confirm the time complexity by noting that the outer loop runs n iterations, and the inner loop runs at most I iterations for each value of I, resulting in a total sum of n times n-1 divided by 2, which simplifies to O(n²). Since each operation in the inner loop is constant time, the overall time complexity remains O(n²). Now let's consider the best, average, and worst-case scenarios for this problem. In all cases, the algorithm involves iterating through the same loops with the same structure. This means the time complexity remains O(n²), and the space complexity remains O(n), regardless of the input size. There are no variations in the number of operations based on specific cases. In conclusion, the dynamic programming solution offers a significant improvement over the brute force approach. It reduces the time complexity from exponential O(2 to the power of n) to quadratic O(n²), and the space complexity to O(n). This makes the solution much more efficient and scalable for moderate values of n. When solving the 4 keys keyboard problem, there are common mistakes that can trip you up if you're not careful. First, many fail to recognize the optimal copy-paste pattern. Instead of repeatedly typing or copying at regular intervals, the best strategy often involves making a single large copy and then pasting multiple times. Misunderstanding this can lead to suboptimal results. Another common issue is misunderstanding the key press limit. Every operation, including Ctrl-A and Ctrl-C, counts as one key press, so exceeding the given n will invalidate your solution. Brute force is another pitfall. While it might seem straightforward to explore all possibilities, this approach quickly becomes computationally expensive due to its exponential complexity. Without leveraging optimization techniques like dynamic programming, brute force simply isn't practical for larger values of n. Finally, incorrect base case handling is a frequent source of errors. For instance, failing to initialize the smallest cases, like DP0 and DP1, correctly can cause cascading issues throughout the solution. Remember, the first few key presses can only result in typing indirectly, so those cases need special care. Another challenge is overcomplicating state transitions. For example, tracking excessive details like the exact clipboard content at every step can make your code unnecessarily complex. Instead, focus solely on maximizing the number of A's on the screen. Simplifying the state makes the problem more manageable. A key insight to keep in mind is that the problem involves a repetitive sequence of operations: type, select, copy, and paste. The real challenge is figuring out the most efficient order and timing of these operations. For larger n, the best approach is to maximize the number of pastes after a single copy operation. This drastically reduces the solution space. Dynamic programming is an excellent tool here. By using a 1D DP array, where DP, I, represents the maximum A's achievable with I key presses, you can systematically calculate the best results. The state transition involves iterating backward to find the optimal point to copy. Lastly, it's important to understand the trade-offs in complexity. Brute force has a time complexity of O(2 to the power of n), which is infeasible for larger inputs. Optimized dynamic programming reduces this to O(n²), making it much more efficient and a great strategy to discuss in interviews. The 4 keys keyboard problem also shares similarities with other well-known dynamic programming problems, making it a great opportunity to build transferable skills. For instance, LeetCode 70, Climbing Stairs, involves identifying optimal subproblems, which is a core principle in this problem as well. LeetCode 279, Perfect Squares, uses a similar DP approach to minimize the number of operations, which can help you think about how to optimize keypress sequences. LeetCode 198, House Robber, is another great example, as it focuses on maximizing a result under specific constraints, much like how we aim to maximize the number of A's while staying within the keypress limit. Lastly, LeetCode 300, Longest Increasing Subsequence, introduces the concept of identifying optimal transitions in a constrained sequence. These problems all reinforce the importance of breaking down a problem into smaller, manageable parts and optimizing transitions between states. There are alternative approaches you can consider for this problem, though each comes with its own trade-offs. A greedy approach, for instance, aims to locally maximize the number of A's at every step. While this can be faster in terms of runtime, it often fails to find the global optimum because it doesn't account for long-term gains from strategic copy-paste sequences. Recursive backtracking is another option, where you explore all possible combinations of operations. This guarantees correctness but is computationally expensive, resulting in exponential time complexity. For those with a mathematical inclination, recognizing certain patterns can offer insights. For example, when n becomes very large, the growth of A's tends to be approximately exponential. This understanding can sometimes help derive a closed-form solution for smaller cases, eliminating the need for iterative computation. However, this approach requires deeper mathematical insight and may not always be practical in an interview setting. Each method has its strengths and weaknesses, so choose the one that best fits the problem context and constraints. Thank you for watching. In this video, we explored the 4-keys keyboard problem, broke it down step by step, and applied dynamic programming to find the optimal solution. Remember, dynamic programming is a valuable skill for solving optimization problems, so keep practicing. If you enjoyed this, don't forget to like, subscribe, and stay tuned for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!